All right, this is the review I think this is actually a quiz, but basically we're covering chapters 1, Intro to Derivatives 2.1 and 3.5. One thing that's not really covered much on this review is that rectilinear packet, so make sure you go back and look at that. Start with limits. So find the following limits. The limit as x approaches 5 on the right. So I need to number these tick marks down here, otherwise I will mess this up. So 5 on the right is up here. That limit is equal to infinity, does not exist. If you know the direction in which the limit is going, make sure you say that like infinity. 5 from the left, that graph is headed to negative infinity. Does not exist. This horizontal asymptote, by the way, does not stop this graph. It does continue down here. Horizontal asymptotes are just to indicate end behavior on the as x approaches negative infinity or infinity. So what is the limit as x approaches 5? It does not exist. And it's not because the left is not equal to the right. It's because g of x is unbounded at x equals 5. All right, now we want the limit as x approaches 1 from the right, so negative infinity. Again, that limit does not exist. We're just telling you which direction it's headed. The limit as x approaches 1 from the left, also negative infinity, does not exist. Now, because both of those limits are headed to negative infinity, as we approach 1 in general, we can say negative infinity, but that answer still does not exist. And on this one, because the graph is unbounded in both directions, I can also still just say g of x is unbounded. At x equals 5. The limit as x approaches infinity, so trace to the far right, you would be on this branch heading this way. So that's 1, 2, 3, 4. So that limit is equal to 4. That limit does exist. The limit as you approach negative infinity, so you're on the far left branch and you're tracing this way, that's negative 1, negative 2. That limit does exist. And the limit as x approaches 3, so from both sides, if you're approaching an x coordinate of 3, you're hitting 4. Write the equations of all vertical and horizontal asymptotes in the diagram. Okay, that should be easy. So vertical asymptotes have to have equations where it's x equals because they're vertical lines. So we have x equals 1 and x equals 5. I'm okay with you separating them by commas. Horizontal asymptotes, y equals negative 2 and positive 4. Sometimes they ask you to use limit notation to describe horizontal asymptotes. That's what they were doing in problems 7 and 8. So that would be what I would answer if the problem said use limit notation to describe asymptotes. All right, find the following limits. So you can do this using our analytic rules. You can sketch graphs if you want, however you need to find these limits. So always think about plugging in direct substitution first. Not sure what this little plus sign, what's going on there. I don't know. So ignore that little plus sign there. Okay, so the limit as x approaches 2 of x plus 3 over 2. So that gives you 5 over 0. So I know this is unbounded. I want to know if I'm approaching 2 from the right, in which direction is it unbounded? So say you had 2.1 minus 2. That would leave you with 5.1 over 0.1. That's a positive over a tiny positive. So you're heading toward positive infinity. 5 divided by, if I made this more extreme, divided by 1/1,000,000th is going to be 5 million. And so you're heading to positive infinity. Below that, if we approach 2 from the left, say you've got 1.9, that's going to make this a positive on top and a little tiny negative decimal on the bottom. So again, think of like 4.9 divided by 1 millionth negative, it's going to be negative infinity. The limit as x approaches -1 from the left. So here, if I plug in -1, again, I get -1 squared over 0. So it's always negative on top. If you're approaching -1 from the left, think about number lines here. So this would be like -1.1 plus 1. So you're going to get this always negative x squared divided by a little tiny negative. That's going to come out positive infinity. The limit as x approaches -1 to the right. So -1 to the right, that'd be like -0.9. So now you've got this negative x squared, which is getting divided by this tiny little positive, -0.9 plus 1. So that's a negative divided by a positive. That's going to be negative infinity. So what about approaching -1 in general? This limit does not exist. Because the two directions don't agree, I can't assign one or the other to it. This limit does not exist because the graph is unbounded at -1. These limits all do not exist either, by the way. My reason for all of them would be unbounded, but I'm just clarifying on this one. Okay, what about this one? If we plug in -3, we would get 0 on top, and 9 minus 6 is 3. Oh, no, wait. Yeah, 9 minus 6 is 3. 3 plus 3 is 6. So if I just do direct substitution in this, I think I get 9 minus 9 over 9 minus 6 plus 3. Isn't that 0 over 6, which is just 0? So direct substitution worked on that one. If I plug in 5, I get 1 over 0 squared. Now, this is squared, so this is 1 over an always tiny positive. So this on either side of 5 will be a limit where the graph approaches infinity. And again, that limit does not exist. The limit as x approaches 2 from the left. So here we have 3 plus 2 from the left would be like you're plugging in 1.9. So that's going to be 1 divided by a negative, so negative infinity. Any constant, no matter how large or small, plus or minus infinity, is equal to that infinity. So negative infinity. This limit does not exist. 15 divided by tangent of x. Now, tangent of x is undefined. So you can't say, oh, it's 15 over undefined. That doesn't make any sense. But remember, we have some trig identities that we need to be able to work with. You need to know your reciprocal identities, your quotient identities, and Pythagorean. Those are the biggest ones. And so instead of 15 divided by tangent, I can rewrite this as 15 times cotangent x. And that's helpful because direct substitution here, cotangent of x is equal to 0 rather than undefined at tangent. So that's just equal to 0. All right, and then final one of these limits. So I have x over 1 minus 1. So 1 over 0 squared. Again, this is positive and this is positive tiny. So that's infinity minus 2 million. So whether this is infinity minus 2 million or infinity minus 0.2, the answer is still infinity. It doesn't matter how much you add or subtract to infinity, you're still going to have infinity. So this limit does not exist. All right, on to the next section. Find the equations of all vertical asymptotes. Vertical asymptotes happen when the denominator is undefined. So we need to set x squared plus 2x equal to 0, which means we should be factoring this. If any of these factors cancel out with what's in the numerator, then it's no longer a vertical asymptote, it's a hole in the graph. So vertical asymptotes are x equals 0 and -2. For this one, this is x plus 3, x minus 3. So vertical asymptotes, x equals plus or minus 3. for this one, I can factor this, x minus 5, x plus 1. So here's a scenario where h of x simplifies to 1 over x minus 5. So the only vertical asymptote is x equals 5. X equals negative 1 is a hole in the graph. This one here, I can factor the numerator a little bit, factor out an x, cancel out x plus 2's. So t of x can be simplified to just be x. By the way, when you simplify this, it's 1 over x minus 5, but x can't equal negative 1. Or this is x, but x can't equal negative 2. That's not a big deal, but it's just sort of like, we're not just getting rid of that expression. It's still a discontinuity. Anyway, because there is no x remaining in the denominator, this graph looks like the line y equals x, and there's just a hole at negative 2, negative 2. So there are no vertical asymptotes for this one. And for cosecant x, remember cosecant x is undefined when sine x, its reciprocal, is equal to 0. So when is sine equal to 0? Think about your unit circle again. Remember all these? Hopefully, I'm drawing it out just in case, but hopefully you remember all of this. Sine is the y-coordinate, so equal to 0 on the left and right values, which would be x equals 0, and pi, if I kept going another trip around the circle, 2 pi, 3 pi, 4 pi. How do we write that? We would say, well, there are vertical asymptotes at every multiple of pi. So we can say k times pi, where k is an element of the integer number set. You'd say n times pi, but it's important that you make some sort of notation that k is an integer. You can write out the words, or you can use the math notation here. Given that f of x is this piecewise function, find a so that f of x is continuous on R. So in a piecewise function or any function, if I see something that can be factored and simplified, I want to do that right away. Because if we need to plug into this and we get 0 over 0, remember that's an indeterminate form and we need to keep working on it. So this factors into x minus 4 times x plus 3 over x plus 3. So really this top equation is just x minus 4 if I have to try plugging negative 3 into it. All right, so what does continuity mean? Always start with the definition of continuity. Doesn't matter which side you do this on, but you can say, okay, so that means that the limit as x approaches, oh no, is this 3 or negative 3? It should be negative 3. Okay, so the limit as x approaches negative 3 of x minus 4 is supposed to equal f of negative 3. So this should say x equals negative 3 here. That's where the discontinuity is. All right, so that means that I plug negative 3 into the x minus 4 expression, so I get negative 7. And I plug negative 3 into the x in this expression, so that's negative 6 minus a, because remember, you're solving for a. And then solve this for a. So I'm going to add 6 to this side. If negative 1 is negative a, then a equals 1. All right, so same idea for this one. Given g of x has 3 parts to it, there's nothing to simplify in here. Find the values of a and b so that g of x is continuous for all real values of x. So there are 2 breaks in this graph. They happen at negative 2 and 5. So we need to make sure that the graph is continuous there. So continuity would mean that the limits and the function values are equal. So I want to start with saying the limits will have to be equal. So let's say, well, I guess it really doesn't matter. So let's say that the limits as x approaches negative 2 of g of x, but I want to use the piece that of g of x is equal to g of negative 2. How do I know which piece is which? So start with g of negative 2 because that's clearly defined for us. So g of negative 2, you have to be in the middle here. So you're putting negative 2 in for that x. So negative 2 times b minus a. That's all I can do so far for g of negative 2. And then that means that the piece that I use for the limit is the other side on x approaching negative 2. So I plug in negative 2 in for this x. So that's negative 2a plus 1. And I can't solve anything with this, but I can at least like combine some like terms. So if I add a to this side, I get negative a plus 1 equals negative 2b. And maybe I want to get my a's and b's together. I don't really know at this point. I'm just going to say 1 equals a minus 2b. You don't have to take it that far. I'm not sure which line will be most useful yet. And then we need to also do this on the other side. So we need to also say the limit as x approaches 5 of g of x needs to equal g of 5. So again, start with g of 5. So that's plugging 5 into the middle equation. That's 5 times b minus a. And then plug 5 into the bottom equation. So x minus 5, that would be the limiting. Oh, no, sorry. 5 minus b. I do that a lot. Make sure that you're double checking. You're plugging in for the x, not the a or b. And then we can combine this a little bit. So we can add b over to this side. So 5 equals 6b minus a. And I think we can do a nice little system of equations here. So let's see. A minus 2b equals 1. You could also use substitution. I'm just noticing I've got an a and a negative a the way I rearranged things. So all these skills, this is like way back from probably Algebra 1 days, solving a linear system of equations. Add these two equations together, you get 4b equals 6, b equals 3 over 2. 6 over 4, 3 over 2. If that's b, then I can go back and find a. So I'm just going to use the red equation. So if it's 1 equals a minus 2 times b, which is 3 over 2, 1 equals a minus 3, I add 3 over, I get a equals 4. Okay. Given this piecewise function, which I see can be simplified, so I'm going to do it right now. Factor an x out of the top and an x out of the bottom. So we can really simplify this to x minus 3 over x plus 1. State true or false. So does f of 0 exist? That is true. F of 0 is equal to negative 1. That's defined in the piecewise function. Does the limit as f of x approaches 0, as x approaches 0 of f of x exist? So let me do this informally. So the two pieces are top and bottom equations, left and right. Go ahead and plug 0 into the simplified version here. So if you do that, if you plug 0 into that, you get negative 3. If you plug 0 into this side, you get negative 3. So yeah, the limit exists. The limit as x approaches 0 of f of x is equal to negative 3 on both sides. F of x is continuous at 0. Well, if that's true, then the limit has to equal the function value, and that's not true, so false. And that's because f of 0 is not equal to the limit as x approaches 0 of f of x. In other words, 0 is not equal to negative 3. F of negative 1 exists. Can I plug negative 1 into the function? So negative 1 is an x value that's less than 0, so I plug into the top piece. If I plug that in, I get negative 4 over 0, so that's false. F of negative 1 equals negative 4 over 0, which is undefined. The limit as x approaches negative 1 exists. That's false because negative 1 is a vertical asymptote of this piece of the function. So I'm going to write f of x is unbounded. So that limit can't exist. Unbounded at x equals negative 1. F of x is continuous at negative 1. Well, that's not possible. If the function doesn't exist there and if it's unbounded, that's false. Because f of negative 1 is no solution. If you found any discontinuities in part C or part F, label them as removable or non-removable. So let's see. So in part C, x equals 0 was a discontinuity. So we have to figure out, is it a hole in the graph, or is it a jump in the graph, or is it just like a vertical asymptote or something. So remember the way this graph is, I don't know the exact shapes, but f of 0 is -1. And then the graph is approaching -3, like whatever it looks like. I'm just making something up. So is that a removable or a non-removable discontinuity? That's just a hole in the graph. We could correct the function value and plug it back in here. So if it's just a hole in the graph, then that's removable. So x equals 0 is a removable discontinuity. The other discontinuity was at -1. We said in this first piece, even after you simplify this, there's a hole at 0, okay, but then there's this vertical asymptote here. So vertical asymptotes are non-removable. So x equals -1 is a non-removable discontinuity. All right, find the following limits. These are all limits at infinity, so we should be thinking of horizontal asymptotes. All right, so this is a tie. In the long run, the -3 and the 1 do not matter, and this will basically divide out to be 2x over 4x. So this limit is equal to 1/4, what the horizontal asymptote is. This is a bottom-heavy function, so in the end, in the long run, these extra terms are going to be very insignificant compared to their higher degree terms. Bottom heavy means we're going to be approaching 0 because the bottom with large numbers will grow much faster than the top. Final one's top heavy. The top is growing much faster than the bottom. So that graph will continue to grow without bound, infinity. Remember to study your rectilinear motion, meaning know the position versus velocity versus acceleration, finding areas and slopes and all of that stuff. So make sure that you work back through that packet or maybe watch my video or something going through it. Find the derivative of f of x at x over x of f of x equals x over x plus 2 using the limit definition. So memorize this formula. Now we're going to use h's because delta x's are kind of obnoxious to write. But make sure that you memorize the difference quotient and that you're taking the limit as h approaches 0. So f prime x equals the limit as h approaches 0 of, so I'm plugging x plus h into this, it's x plus h over x plus h plus 2 minus f of x all over h. Write the entire difference quotient. Don't drop your limit notation until the very end. We can't plug 0 into this right now because we would get 0 over 0, and that would be indeterminate. So what we do is multiply by the denominators that we see, because that will clear out this complex fraction and should leave us with something that does work with direct substitution. So I clear these out by multiplying by the least common denominator on the top and the bottom, because I'm just multiplying this fraction by 1, just a very fancy version of 1 that's going to clear out all the ugly fractions. So when I do that, I'm keeping my limit notation. So if I multiply this over here, the x plus h plus 2 will cancel, and I'll have x plus h times x plus 2. And if I do that here, I will have minus x times x plus h plus 2. In the denominator, nothing cancels, so you just throw it all together. H times x plus h plus 2 times x plus 2. Okay, and then let me change colors so this doesn't jumble together. Then we get to do some fun math. Keeping limit notation, this becomes x squared plus 2x plus hx plus 2h. Did I get them all? X squared, 2x, hx, yeah. And then minus x squared minus xh minus 2 Do not FOIL anything in the denominator together. We're hoping that we can cancel this h out somewhere. Okay. All right, so x squared's canceled. Should be anything without, this is a minus 2x. Anything without an h should cancel. So plus 2x, minus 2x. Everything else has an h. The reason that's going to work out is because this h out here can cancel with all of these, because it says if you factored an h out and then you're canceling it. So now I just have x plus 2 minus x. Oh, I could have canceled those originally. Okay, whatever. And then this h canceled, so I've got x plus 2 plus h times x plus 2. Now try plugging in h equals 0 again. You have 2 on top. Now you have x plus 2 plus 0 times x plus 2. That's x plus 2 squared. That is, not h prime, sorry, f prime of x. That's our equation. Now, in a few days, we are going to learn the shortcuts for derivatives, so we don't have to go through all this fun stuff, but we do need to know it for our AP test. So that's where derivatives come from. Without calculating values, put less than, greater than, or equal to in the blank. So this is the formula for an average rate of change, which is also known as the secant slope between those 2 points. So here's -4, here's -1. Take a look at this slope. So that slope is what we're looking at for the AROC versus f prime at -1. So f prime is the tangent slope at -1. Which slope is bigger or smaller? Now, both of them are negative. So remember, like -4 is actually less than -1. So this steeper negative slope is less than this less steep slope. So this slope, the AROC slope, is less than the shallower slope here. Okay. Draw a graph of a function f of x which satisfies the following conditions. We could have different graphs for this, but they're probably all going to be fairly similar. First thing to do for sure is plot the point you're given. That's foolproof, right? So 1, 2, 3, 4, 1, 2. Here's the point we all have to have. We all have to have that. F prime of 4 is 0. So I like to dot in for myself a little tangent slope that's horizontal. And then what does this mean? F prime is less than 0 when x is less than 4. So on the left, f prime being, I said less than, I meant greater than. F prime being greater than 0 means f should be increasing. If the derivative, if the slope is negative, if the slope is positive, the graph should be going up. So to the left, the graph is increasing, and then to the right, the graph is decreasing because f prime is less than 0. So if you've got negative slopes, you've got a decreasing thing. So let's see. We have an increasing graph for a while, and then we round out at decreasing. I know it has to be rounded like this instead of like an absolute value because f prime of 4 is equal to 0 rather than being undefined at a sharp turn. All right, so increasing, decreasing, that's our value. Write an equation of the tangent line to f of x at x equals 3 if f of 3 equals -2 and f prime equals 1/2. So this is the point we need, and the derivative is the slope we need, and all we have to do is write a point-slope equation. So y minus -2 equals slope times x minus 3. That's it. I'm not going to rearrange that unless I'm told to do so. Okay, for this one, given f of x equals x squared minus 2x, approximate f prime of 4 by finding f of 4 and f of 4.1. So how are we going to approximate a tangent slope? We will find the secant slope using points that are close to 4 and a point very close to it, and that's going to be our approximation. So let's find the average rate of change, the AROC, between those 2 points. F of 4.01 minus f of 4 over 4.01 minus 4. All right, I'm not going to mess with, let's see. I don't know, would this be calculator or non-calculator? I don't know, whatever. But as you can see, it's the end of the school year and I don't feel like doing math right now. So actually, I'm going to do this. F of x is equal to x squared minus 2x. And then I'm just going to do, why don't we just really let the calculator do all the stuff for us? 4.01 minus f of 4 over 0.01. I can do that math. So 6.01 is our approximation. About equal to 6.01. So what we were saying is our estimation for f prime of 4 is about equal to 6.01. Maybe it's exactly 6. Find f prime using the limit definition and then use this answer to find the exact value of f prime of 4. I don't want to do it that way. Instead, I want to use the alternate form, which says when you're trying to find f prime of c, like you're trying to plug a number into the equation, not just find the equation itself, you can use the limit as x approaches c of f of x minus f of c over x minus c. All right, so we want f prime of 4. So we're going to take the limit as x approaches 4 of x squared minus 2x, that's f of x, minus, what's f of 4? 16 minus 2 times 4, it's 8. So minus 8 over x minus 4. Now, if you plug 4 in right now, you're going to get 0 over 0, but this can be factored. It's equal to the limit as x approaches 4 of, this is x minus 4, x plus 2. So really just of x plus 2. And go ahead and plug 4 into that. F prime of 4 is then equal to 6. Seems reasonable. My approximation was 6.01. The actual value is 6. That's good. We're on track for that. You could find the equation for f prime of x and then plug 4 into it. But remember, this is what you should use if you're evaluating a derivative at a number. You can't use this form if your goal is to find f prime of x. But if your goal is to find f prime of a number, use this form always. State the 3 reasons a derivative will fail to exist at x equals c and draw a graph to illustrate your understanding of each. So I'm going to draw the graph up here. So scenario 1 is it doesn't matter what order you do these in, f of x is unbounded at x equals c. So what might that look like? Here's c. Here's f of x being unbounded. Okay. Scenario 2, the limit as x approaches c of f of x does not exist. Now that could be because of being unbounded, but I want a different scenario. So that would probably be because the left doesn't match the right here. So we could say if there's like a, actually, no, I'm sorry. Let me generalize this more. Sorry, I'm in limit mode. How about f of x isn't continuous? Because that catches everything at x equals c. So that could be unbounded, or that could be a jump in the graph, something like that. Or that could be where the limit exists, but the points, the f of c point is something different, like this. And then this. There's no derivative at that point then. Okay, number 2 is, so we have some sort of discontinuity, then no derivative. If there's a sharp turn, think of an absolute value graph or something, that sharp turn at c. And that's because, again, if you did the derivative graph wouldn't be continuous. The derivative graph would jump from, say, -4 to +4. There'd be a jump or a gap in there. And then the third scenario is f of x oscillates at x equals c. It has to be real oscillation. Like you zoom in and it still looks like this. So this happens usually when trig is involved and some crazy expression is inside of the trig function. Use the alternate definition of a derivative. This is the one I was using before to find f prime of c. So I would want you to do it in any scenario. You're not going to be directed to use the long way to find f prime and then plug a number into it. So f prime of 4 is equal to the limit as x approaches 4 of radical x minus f of 4, which is 2, over x minus 4. Now, if I plug 4 into this, I get 0 over 0. So what do I need to do in this scenario? If a radical is involved, I'm going to multiply by the conjugate of the radical on the top and the bottom. And then as I simplify this, I'm going to keep my limit notation until the very end. So when I FOIL these two conjugates together, I get x minus 4. And then I don't actually distribute anything together. I just write x minus 4, the quantity, times radical x plus 2. These x minus 4s will cancel. So this is actually just 1 over radical x plus 2. And now I can plug 4 into that, and I get 1 over radical 4 plus 2. So f prime of 4 is equal to 1 over 4, so 1/4. For this one, when c is -2, we want to know what f prime of 4 is. So f prime of 2, f prime of -2, there we go. It's the limit as x approaches -2 of x plus 2 to the 1/3 minus, when you plug -2 into this, you get 0 over x minus c, so x minus -2, be plus 2. Now the minus 0 can go away. If I plug -2 into this, I get 0 over 0. But if I just use my exponent rules, let me get my pen to work again. If I just use my exponent rules on this, my pen doesn't want to work. Hold on. Okay, let's see if I can get the pen to work. There we go. Okay, so I can use exponent rules on this. X plus 2 to the 1/3 over x plus 2 to the 1st is now 1 over x plus 2 to the 2/3, right? 1/3 minus 1 is -2/3, so I sent it down there. Now if I plug in -2, I get 1 over 0. And it's 0 to the 2/3, so that means like cube root of whatever you got squared. So you're squaring this quantity, whether it's positive or negative, it will come out positive, and then you're taking the cube root of that. So f prime of -2 is no solution, and that's because f of x is unbounded at x equals -2. I only care which direction it's heading if I were trying to say, what is this limit? This limit is infinity then. All right. A rock is thrown upward from a 7-foot platform with an initial velocity of 15 feet per second. Here's the position equation and the graph. What is s of 0 and s of 2.5? So are we using a calculator for this? I guess we're going to use a calculator. S of 0, I don't need. So S of 0. Oh, actually, no, I don't need a calculator because it's actually on here. So S of 0 is 7 feet. And S of 2.5 sure looks like it's 27.75. I'm not going to take the time to confirm on my calculator. Describe the difference between average velocity and instantaneous velocity. So this is not with respect to this problem, it's just in general. So average velocity is the change in position over the change in time, also known as the secant slope. Instantaneous velocity is the how do I want to put this? It's the change in position. Well, let's see. It's the velocity at a specific time. So let's see. Change in position at a single time. Am I saying that right? I feel like I'm overthinking this. It's the tangent slope. So average velocity is, what was your speed with direction from 0 to 5 seconds? And instantaneous velocity is what was your speed with direction at 5 seconds? What is the instantaneous velocity at 2.5? So at 2.5, that's the vertex of this quadratic. So S prime of 0, which is also V of 0. Sorry about my pen here. Oh my gosh. Which is also, okay, hold on. Those should be 2.5s. I'm really having technical issues here. S prime of 2.5, is equal to V of 2.5. And I know that's equal to 0 without doing any math because that's the vertex of that quadratic. And what should my label be on this? Feet per second. Find the average velocity from 0 to 2.5. Draw a geometric representation of what you found on the graph. So I'm going to do that first. So here's 0, here's 2.5. I'm about to find the slope of that line. So average velocity, average rate of change is S of 2.5 minus S of 0 over 2.5 minus 0. That's 27.75 minus 7 over 2.5. That's 20.75 over 2.5, whatever that is. Honestly, on the AP test, you don't have to simplify stuff. So I'm leaving it like that. What is your average velocity from 0 to 1? So that should be, again, average velocity is average rate of change. S of 1 minus S of 0 over 1 minus 0. Looks like S of 1 is 19 minus 7 over 1. That is 12 feet per second. What's the instantaneous velocity at 1? So this tangent slope, I'm going to need to do a bit of finding, right? So I want to find S prime of 1. And we don't know our shortcuts yet. So I'm going to use my alternate form of the limit definition. I'm going to say, well, that's the limit as x approaches 1 of S of t minus S of 1 over t minus 1. So that's the limit as x approaches 1 of negative 3t squared plus 15t plus 7 minus 19 all over t minus 1. This should be a t, not an x. Sorry. T approaches 1. So this is negative 3t squared plus 15t minus 12. Let's factor a negative 3 out of that to see if it factors. Yep, I get t minus 1, t minus 4. The t minus 1s can cancel. So if I take this limit, I get negative 3. Oh, well, that's not right. Negative 3. Did I mess up my math somewhere? Okay, let's see. We factored out a negative 3. Sorry. Factored out a negative 3. I got positive t squared. Did I get minus 5t? Because that says plus. Somebody catch my mistake for me. What am I doing? Minus 19. Oh, I don't see the mistake. T equals t minus 1 cancels. Plug 1 into that. This does not look like a negative 3 slope, does it? Let me see what my official key said. What did I do years ago that I'm not doing right now? Find the right problem. Where'd it go? Okay. Oh, yeah. Okay. I factored a negative 3 out. I can't totally forget about that. This is what I get for not clearly writing my work. It's negative 3 times negative 3, which is 9. That looks better. Feet per second. All right. Maybe you caught that for me and were yelling at the video. I don't know. Good job if you did. All right. Graph this equation. Zoom in at 1. What does it mean when we say the tangent line is locally linear to S at t equals 1? So, let's check that out. So let me graph S of t equals, that should say negative 3t squared plus 15t plus 7. Not a trick question here. Zoom way in at 1. So here it is. Now, if I don't show you the equation, can you tell that this is a curve versus being something linear? I would say no, I can't tell. So all this is saying is, as you zoom in on any points, the reason that we often say use a tangent line to approximate a value, if I put a tangent line at this point here at 119, and then I use the linear equation I get off of that tangent line to approximate this value here, they're going to be very close, because when you zoom in very far and you don't stray too far from the point of tangency, your tangent line is a very good approximation usually of the curve that you're looking at. Okay, so I'm not going to write what all of that means, but I'm sure I have something posted. But yeah, as we zoom in enough, the graph looks linear, so we say it's locally linear at that point. Give the position of S of t. Given this position function, find the average rate of change from 0 to 4. So write this formula out every time for 2 reasons. It's an easy point to score on an AP test if they're giving you a point for that. It also triggers your brain into like what you're supposed to be doing. So let's plug 4 into this. We get 2 times 16 plus 24 minus 1. Minus, plug 0 into this, you get minus 1 for 4. Now this is negative 1 plus 1. So I really just have to do 32 plus 24 over 4, which is 56 over 4. And that's probably something, right? That goes in once, goes in 4 times, it's 14. So find the average rate of change, 14. I don't see any units here. The average rate of change from part A represents, so what does this represent? The slope of the secant line between 0 and 4. Yeah. The slope of the tangent line at some time t. No. The average velocity from 0 to 4. Yeah. Instantaneous velocity? No. Change in position? No, because that would just be s of 4 minus s of 0. Definitely not the derivative. Find the instantaneous rate of change at t equals 4. So they want me to find s prime of 4. So I will use my limits as x approaches 4 of s of t minus s of 4 over t minus 4. Gosh, I keep writing x's when I should write t's. That's the limit as x approaches 4 of 2t squared plus 6t minus 1. And then what do we get when we plugged in 4 before was 32 plus 24 minus 1. So that was 56 minus 1. So that's 55 over t minus 4. Okay. 2t squared plus 6t minus 56. That can cut a 2 out of that. Let me learn lessons from before and not cut too many corners here. I'm going to factor 2 out of this. What's half of 56? 28. T minus 4. Did I mess up again somewhere? Let's see. When I plug in 2t squared, so when I plug in 4, I get 2 times 16 plus 24 minus 1. So 56 minus 1 is 55. Okay. 7 and 4. I thought I screwed up because it didn't factor, but it does. I'm blaming this. Notice the date. This is our last-ish week of school. I'm blaming it on that. Okay, so S prime of 4 is equal to 2 times 11, 22. And again, no labels on this because there's no context to this problem. So that number we just found, the instantaneous rate of change from part C, is slope of a secant line? No. Slope of a tangent line at some time t. It's not really at some time t. It's at t equals 4 specifically. So I'm going to say no about that. Average velocity? No. Instantaneous velocity at t equals 4. So these two, I'm kind of like, yeah, the wording's weird, but okay. The change in position? No. The derivative? This is no because the derivative implies f prime of x equation, and this is not. This is just the number at 4. What was the initial position of the object? Hopefully you don't need this hint, but that's when t equals 0. So way back here, s of 0 would be equal to negative 1. Sketch a graph of s of t using a calculator, then draw the tangent line at t equals 4. Zoom in at t equals 4 multiple times. What happens to the graph? So the function and the tangent line at t equals 4 are, I bet it looks linear, so locally linear, just like we were doing before. We can go ahead and do that graph. Why not? So, because again, we can kind of use this Desmos to our advantage here. So, let's see. Start with s of t, and it was equal to 2t squared plus some other stuff. Where'd it go? Let's see. Oh, okay. 2t squared plus 6t minus 1. And so graph that, and we were looking from 0 to 4. So I've got this zoomed out really weird, so I'm just going to say, put a table in there, s of 0, s of 4. Show me that section of the graph, please. Okay. Now, we did a tangent slope at 4, so this is kind of cool. You can say, I think this should work. We have the points for s of 4, so I should be able to say y minus s of 4 equals, we'll see if it lets me finish this or not, s prime of 4 times x minus 4. It did it. See, it's happy. So this is kind of cool. I didn't have to actually calculate any of this, and yeah, it definitely looks like a line tangent to the graph. And when I zoom way in, I can hardly tell any difference between these two graphs. Let's change the color of one of them just to see if we can make things, yeah, nope, no idea. These things look the same. All right, that's pretty cool. remember to go back and look over your, there's more to do. Remember to go back and look over your position and velocity functions as well as we move on to this final page. Draw the graphs of the derivatives given the functions. So the derivatives, I'm going to do this to the left, or to the right. So remember, derivatives are the slopes. What's happening here? We have a slope of 0. This is a slope of, we're going up 1, 2, 3 over 2. This is a slope of 3 over 2. And this one's a slope of down 1, 2, 3, 4, negative 4 over 1. So when I do this, open circles where the graph changes. So 0 until here. And then a slope of positive 1.5. So I'm going to put that here until I get to here. Oh, gosh. Until I get to here. And then a slope of negative 4. So like down here. That's that first one. Now B, this is like super negative slope. Still negative, less negative, 0. And then positive, positive, super positive. And then it starts leveling out again, back to 0. And then little negative, more negative, super negative. So what does this graph look like? Let me label these. Okay, where are the zeros? There's one at 0, and there's one at 1. So I always put my zeros in first. That's where the velocity or derivative is 0. And then it started out super negative and got close to 0, so something like that. And then it got positive for a while and came back to 0, and then down here. This is a very ugly graph, but that's my rough sketch for f prime. Now this one for part C, we are starting out pretty much 0 and then getting negative, 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 and then less negative, back to 0. Little positive, positive, super positive, less so until we get back to 0. So again, you're not actually hitting 0 on the ends. You are hitting 0 in the middle. You're approaching 0 on the ends. Otherwise, you're negative. So we're starting off kind of negative. We get really negative, and then we come back to 0. Then we get positive, really positive, then we come back to 0. Something like that. For this last one, there's a discontinuity at negative 1. So our derivative graph should also not be continuous there. We're sort of 0 and then positive, positive, really positive, really positive, really positive. So like 0 to super positive that way. And then here, super negative, less negative, less negative, less negative, 0. So on this side, super negative until we get kind of closing back to 0. Write 3 different derivative notations. So we have f prime of x, dy dx, or what's the third one? I don't know. d f of x dx, something like that. True or false? If a function is continuous at c, then it's differentiable at c. False. Just because you have continuity, it does not imply differentiability. Think sharp turn. An absolute value graph is continuous, but it's not differentiable at its vertex. Now, the other way around is true. If a function is differentiable, then at c, then it's continuous at c. So that's true because remember, we have different qualifications have to happen. If a derivative exists, then the function must exist, the limit must exist, and it must be a smooth, not a sharp turn. So that has to be true. If a function has derivatives from both the left and the right at c, then it's differentiable at c. That's false. It goes back to the continuity thing. Just because you have, let's do this. Just because you have a limit right here doesn't mean that the graph exists at c. So there can't be a derivative at a place where you have a discontinuity. Continuity implies differentiability. That's the same thing as A. That's false. But B is the same thing as E. Differentiability implies continuity. That's true. There's no way you can have a derivative if the function isn't first continuous at that point. All right, that finishes that review. That was a long review. Hopefully you feel pretty good about, pretty prepared, I should say, about the test or quiz tomorrow. You will do just fine if you got through this and understood. Feel free to go back and practice homework assignments that you found challenging.